The device sitting on millions of rooftops right now was classified military radar technology in the 1980s. The United States Navy spent hundreds of millions of dollars per installation. SpaceX ships the consumer version to your door for $599, and you self-install it in 15 minutes. And what it does should be physically impossible. Before the engineering, you need to understand the nightmare this replaced. For decades, if you lived outside a major city, your internet options were basically two: a slow copper phone line or satellite internet from companies like HughesNet and Viasat. And that satellite internet came with a fatal flaw no amount of marketing could hide: 600 to 800 milliseconds of round-trip latency. Every time your device sent a request, loading a page, joining a video call, uploading a file, the signal had to travel 35,786 kilometers up to a geostationary satellite parked in fixed orbit, then 35,786 kilometers straight back down. 70,000 kilometers round trip, at the speed of light. For video calls, that delay turned every conversation into two people awkwardly talking over each other. For gaming, it was unplayable. For anyone running a business remotely, it was a career ceiling with no workaround. That was the status quo for a massive chunk of the planet. And then a pizza box arrived and broke the equation entirely. The Starlink Dish, officially called the User Terminal, affectionately nicknamed Dishy McFlatface by early SpaceX employees, is not a better version of the old satellite antenna. It is a completely different category of technology built around a completely different idea. Traditional satellite internet parks its satellites at 35,000 kilometers in geostationary orbit, so they appear stationary in the sky. Starlink does the opposite. 10,397 active satellites orbit at just 550 kilometers, close enough that the signal round trip shrinks from 70,000 kilometers to roughly 1,100. The result? A median latency of 25.7 milliseconds in the United States during peak hours. That is approximately 1/30th the lag of old satellite internet, close enough to fiber that for most applications, video calls, gaming, streaming, cloud software, you genuinely cannot tell the difference. But this creates an engineering problem that sounds unsolvable. At 550 kilometers altitude, a Starlink satellite moves at 27,000 kilometers per hour, fast enough to cross your entire field of view in under 3 minutes. A traditional dish would need a motor constantly spinning and tilting to follow it. So get this, the Gen 3 Starlink Standard Dish has no motor, not a small motor, not a quiet motor, 0 motors, none at all. Inside the panel, roughly 58 by 51 centimeters, weighing just 2.9 kilograms, sit approximately 1,280 individual antennas arranged in a hexagonal honeycomb pattern. Each one is a tiny aperture-coupled patch antenna built into a 6-layer circuit board. Alone, each one is essentially useless. Together, they form what engineers call a phased array. Here is the physics. When all 1,280 elements transmit simultaneously, their radio waves either reinforce or cancel each other depending on direction. By precisely controlling the timing, the phase, of each element's signal, the array creates a narrow, focused beam, just 2 to 5 degrees wide, aimed at a precise point in the sky, with destructive interference canceling out all other directions. To steer toward a different point, the dish recalculates those phases in microseconds. In silicon, 20 beamforming chips and approximately 640 front-end modules run this calculation continuously. The dish also compensates for the Doppler effect in real time, because the satellite is moving so fast relative to the ground. The received frequency shifts just like a passing siren changes pitch. Without real-time correction, the signal drifts out of band within seconds. When the current satellite approaches the 25-degree minimum elevation horizon, the system has already scheduled a handoff to the next incoming satellite, technically capable of switching up to 10 times per second. In practice, handovers happen every 1 to 3 minutes. You never notice, oh my goodness, 1,280 antennas, 0 moving parts, tracking an object moving at 17,500 miles per hour. From a panel you can carry under one arm. The phased array technology behind this was developed by the US Department of Defense for the Aegis radar system, deployed on Navy destroyers starting in the early 1980s. Those installations cost hundreds of millions of dollars each. SpaceX did not invent the physics. They drove the cost down far enough to sell it at a big box retailer. Here are the numbers that put this in context. 10,397 active satellites in orbit as of June 2026. Total network capacity, approximately 450 terabits per second. Median United States download speed during peak hours, 200 megabits per second. Maximum measured by individual users under optimal conditions, around 500 megabits per second. Packet loss under typical conditions, less than 0.5%. Total subscribers, over 10 million across 155 countries. The Dish line currently ships in 4 models. The Mini at $199 draws roughly 45 watts and delivers 100 to 260 megabits per second, designed for backpacks, vehicles, and portable setups. The Standard Gen 3 at $599 for home and business use. The Flat High Performance at $2,500 for vehicle and commercial deployment. Maritime hardware starts at around $10,000. Monthly service runs from $80 for residential plans up to $165 and above for unlimited mobile coverage. Total first-year cost for a typical home setup, $1,400 to $1,800. Not cheap. Transformational for the millions of subscribers who previously had no viable alternative. If you want to understand what is actually happening in the technologies reshaping daily life, not just the headlines, the actual engineering, subscribe. We cover every major development every single week. Hit the bell so you do not miss the next one. Imagine this, a rancher in rural Montana, 60 miles from the nearest town. For 2 decades, satellite internet with 800 millisecond latency made video calls a frustrating joke. Cloud software was unusable. Remote work was effectively impossible. She mounts a 2.9 kilogram panel on a fence post, runs one cable inside to the included router, a single power over Ethernet connection that carries both power and data through the same wire. Opens the Starlink app on her phone. It overlays an augmented reality cone on her camera view, showing exactly which patches of sky need to stay clear of trees and buildings. She confirms the view. Power's on. 12 minutes total. No installer, no alignment tools. The next morning, she joins a video call with her equipment supplier in Denver with 0 perceptible lag. She runs accounting software in real time, pulls live commodity prices on the same connection her son uses to stream high-definition video for school. The satellite overhead when all of this happens is moving at 17,500 miles per hour. She has no idea, and that is exactly the point. That experience is live right now across 155 countries. Research stations in Antarctica, fishing vessels in the North Atlantic, emergency response teams in disaster zones where every cell tower just went down. That is not science fiction. That is the current state of a network that barely existed 6 years ago. Here is where the trajectory points, and the numbers ahead are genuinely wild. Throughout 2026, SpaceX is moving approximately 4,400 satellites from 550 kilometers down to 480 kilometers. Lower orbit means lower latency. Starlink has stated a goal of under 20 milliseconds. And faster atmospheric decay for any satellite that fails, reducing debris risk. SpaceX Vice President of Starlink Engineering, Michael Nichols, announced the reconfiguration on January 1st, 2026. V3 satellites, designed for SpaceX's Starship rocket, will carry over 1 terabit of downlink capacity each, roughly 10 times the current generation. A few hundred of these go operational, and total network capacity multiplies dramatically. The uplink capacity per satellite exceeds 200 gigabits. Crazy numbers. Direct-to-cell is the most disruptive development on the roadmap. Newer satellites carry cellular band radios that allow ordinary smartphones to connect directly to a satellite with no dish required. T-Mobile is the lead US partner. Texting and voice calls from the middle of the ocean on the phone already in your pocket. Competition is arriving. Amazon's Project Kuiper has begun its first batch deployments. OneWeb, now part of Eutelsat, operates a smaller constellation. China has 2 state-backed programs, Guoang and Qianfan, targeting domestic and international markets. None approach Starlink's current scale. The race is real, and it is just getting started. We want to be completely upfront about what this system genuinely gets wrong, because it gets some things seriously wrong. The astronomical community is not happy. 10,000 satellites reflecting sunlight during twilight hours create streaks across telescope images that ruin months of observation data. The American Astronomical Society and the International Astronomical Union have both issued formal objections. SpaceX responded with darker satellite coatings and sunshades. Brightness is reduced. The problem is not solved. Orbital congestion is a documented and serious risk. Starlink represents approximately 69% of all active spacecraft in Earth orbit. A December 2025 in-orbit anomaly destroyed one satellite and generated a debris cloud. The altitude-lowering plan is partly an acknowledgement that at this scale, active debris management is not optional. It is survival. Weather affects performance. Heavy rain and snow reduce speeds by 10 to 30%. The self-heating function that melts snow accumulation on the panel surface adds over 100 watts of power draw when active. Significant for anyone running off solar. And there is a concentration concern that deserves honest attention. 10 million subscribers now depend on a single, privately operated network. The 2022 dispute over Starlink access in Ukraine showed exactly what political leverage over critical communications infrastructure looks like in practice. There is currently no comparable alternative at a remotely similar scale. That is a real structural vulnerability. Here is where we land. A $599 panel on your roof contains the same fundamental physics the United States Navy deployed to track incoming missiles in the 1980s, at a fraction of 1% of the original cost. 1,280 antennas, 0 moving parts, 27,000 km/h satellite tracking, 25 millisecond internet to 10 million subscribers across 155 countries. V3 satellites arrive with 1 terabit of capacity each. Direct-to-cell removes the dish from the equation entirely for mobile users. The constellation is moving lower to push latency toward 20 milliseconds. And the hardware price keeps falling. What sounds like the better deal to you? 800 milliseconds of lag on a geostationary satellite bill, or 25 milliseconds from a pizza box you install yourself in 12 minutes. Here's the question I want you to answer in the comments. Where would Starlink change your life the most? Rural home, boat, RV, off-grid setup, or disaster preparedness? Drop it below. I read every single one. Like and subscribe, and I will see you in the next one.